You don't have to, but if you're all doing clocks, one of the things you're going to need to be able to do is to know when a second has expired. So you're going to have to use, if you're using an 8051 this is, if you're doing an 8051 based system, one of the timers, doesn't matter which one, you're going to need to use to basically increment or to tell you when 1 second has expired. Now, you could configure the timer. Now the problem is, you've got a couple of issues with that. One of the issues is you know that these timers are only 16 bits, and if you're using the on-chip oscillator, unless you've got an incredibly slow crystal, it's not going to take it very long to overflow, much less than 1 second. You know, for example, if you had a 12 megahertz crystal, and remember it divides by 12, so that's 1,000,000 machine cycles per second, the counter counts up, it takes 1/1,000,000th of a second to count. 16-bit counter, the biggest count value you could cope with is 65535 decimal. Or if you like it would overflow at 65536, if you like. And this would be, that's how many machine cycles it would be, because we want 1 machine cycle per count. Well, with that kind of crystal, 1 machine cycle is 1 microsecond, so it would be 65,000 microseconds, or 65 milliseconds is about the biggest count you can support directly from the timer. So the first thing you're probably going to have to do is to use the timer in combination with another register. So what you would do, for example, you might, I don't know, it doesn't have to be any special register, we might say register R7. You could configure this timer so it overflows, rather than at 65 milliseconds, you might say, well, let's get it to overflow at every 50 milliseconds. So this timer, you're going to configure it to overflow every 50 milliseconds. And then you ask yourself, well, how many 50 milliseconds are there in 1 second? Well, that's 20, I think. So what you could do is each time this overflows, you add 1 to what's in R7. You initialize it with 0. And then you keep counting up. When it gets to 19, okay, that's the thing. On the 20th step, you know you've done 20 lots of 50 milliseconds, i.e. 1 second. At that point in time, you would reset this back to 0. And the fact that you've now had 1 second elapse, it would tell you to go and do something with some other bit of code, whatever appropriate for that. Okay, because from 0, so on the 20th step, you do something and then come back to here. Now, you need to know when 50 milliseconds has expired, because you don't want to miss it. Well, you have two choices. You either write a program that keeps checking the flag to see if the overflow's taken place, but I would not recommend you do that. I would recommend that you use timer 0 in interrupt mode, so that when it overflows, you won't miss it, and it will add 1 to this thing. That means that while this is counting, and you're not having to deal with this, you could be going to do something else, like displaying what's on your clock, doing some other useful work. Knowing you have the peace of mind, you're not going to miss the next tick interval, the next 1 second tick. So if you are using an 8051 to do, if you like, to base your clock on it, one of the timers, I would imagine, is going to be used as a part of an interrupt service routine, together with a register. And every so often, this register gets incremented. When the register reaches a special magic value, which is equivalent to 1 second, you might go off and do some other thing. Like you might add 1 to some other register somewhere, that instead of at 57 seconds, you go to 58 seconds or something. So you might have other registers, and they might be binary coded decimal or something else, but these might store minutes, these might store hours. You might have another pair here that stores seconds. So when you get to 59 seconds, and this thing expires again. You add one to here, you realise it's got to 59 or whatever, so you wrap it around to 0, you add one to here, and all that kind of stuff. And once having done that, you're also, in the main program, displaying effectively the contents of these registers, either directly or you're doing some kind of conversion. So now, that's not enough for you in terms of your design and build project, because I think you have to have other functions. But you've got lots of other pins on the 8051 that you can do magical things with. So, and you could have other types of interrupts going on as well. So anyway.
Sweet.
So the stuff that we've been doing on interrupts, if you are going to use an 8051, is going to be very useful to you in design and build. That's all I'm saying. And there are lots of examples in the Mazda book. If you've got that, there's copies in the library. So if you're not sure, there's example code and so forth.
Thank you.
Okay, so we're exactly halfway through the course now, which means for the next 3 weeks we're going to go at double speed almost. Terrifying thought. Mind you, we've got a lot more lectures, so to speak, because generally we're doing 4 lectures per week. Well, 4 hours of lectures per week. Although next week, remember, there is no Wednesday lecture. Just Thursday and Friday next week.
Just late.
But after that, for the next few weeks, there'll be Wednesdays, Thursdays, and Friday lectures. Okay, so this is just a recap of the 8051. I'll go through this quite quickly, because we have done it before anyway. So, the difference between a microprocessor and a microcontroller is a microcontroller is a microprocessor with a number of kind of support functions built onto the same chip. So generally speaking, it can do everything a microprocessor can do. However, given that it's usually used in embedded systems, it tends to have instructions which help it do things like control, like the ability to change individual bits on a port without having to manipulate a whole byte of information. So they tend to have a slightly specialized instruction set. They tend to be simpler in some ways. They don't have usually complex arithmetic logic units and things, but you can get some that are getting more complex these days. They tend to have on board the chip RAM and ROM. The ROM for holding the program memory, and the RAM for holding, if you like, temporary data memory. Okay, and that's just reminding you of these facts. So the ROM is holding read-only memory is holding what we call persistent information, information that we don't want to lose when we switch the power off. The RAM is holding information that we want to manipulate, change, and we don't really care when the power's off. So here's a very generic block diagram of a microcontroller. Nothing special to an 8051 here. So in addition to the actual main central processing unit containing the arithmetic logic unit, we've got RAM for temporary data, ROM for the program memory, and then other peripherals either on the chip or connected to the chip that we can control. Various buses that link all these things together. A bidirectional data bus, an address bus which is basically driven by the CPU to select different things, and then a control bus for special things like signals to read and write. Okay. Now, in terms of talking to the I/O, I didn't invent these terms, they're quite sort of generic. Let's say I've got blocks of pins here that are basically used for input-output. The question is, how do I talk to them? Now I can talk to them in various ways. One way is, if this is my, if you like, my data memory, they could just appear as part of the data memory. So writing to certain locations in the data memory effectively writes to those pins. In that mode of operation, basically the I/O is just like any other memory location. Now it happens to be connected to physical interfaces on the device. But in terms of the memory map, they're just, so this might be, for example, port 2, this might be port 0, this might be port 0, port 1, port 2, port 3. This is in the data memory. So just by writing to these memory locations, effectively, I'm automatically writing to those pins. As far as the program's concerned, it doesn't know that these are anything special. It just sees them as part of the data memory. If you have a processor that regards the pins, if you like, the I/O, as just part of the main memory, nothing special, we talk about that being memory mapped I/O. There is an alternative. You might have the same architecture, but you might have your data memory over here, and then another special places that you can write to that is directly connected to these that is not part of the main memory. And there'll be special instructions to read and write from these locations. There's a differentiation between ordinary data memory and this special memory that's only used for I/O. That type of architecture is known as a port mapped I/O. Port mapped. So there's memory mapped and port mapped. In memory mapped, basically the I/O, just like ordinary memory locations, but because they now feature in the main memory map, those memory locations can't be used as general purpose memory anymore because they're occupied by those special ports. So of the whole memory map, you've lost a little bit of it to map the ports into the main memory. In this other architecture, you've got the whole data memory for just general purpose and a completely separate kind of memory that when you write to, effectively writes to the ports, where you read from, and so on. It's completely separate from it. So all it's saying here is if we go from memory mapped, effectively the I/O is just treated like ordinary memory, but it will actually occupy certain memory locations from the main memory. In port mapped, there's a separate special address space that's only used for ports, and we use special instructions to access that information. As it says here, the 8051 is a kind of bit of both. You can argue it has features which allow it to be port mapped, and it has features which allow it to be memory mapped. In terms of, I'll mention about the MoveX instruction. I've got an 8051 here. And we haven't really talked too much about how to connect it to the outside world, but we've done a little bit. So let's just recap what we remember. A latch. Address high, address low, data. ALE, address latch enable. Do you remember this? Many weeks ago. Effectively, this could be some external device here, some I/O. If you issue something like an instruction like move X into the accumulator, I don't know. No, let's not do that. 12 hex. I think this can be a 16-bit number, by the way, but anyway, let's just... This is going to say go to external data memory location 12, go into that location and put the contents into the accumulator. This kind of instruction is, it doesn't know that this may be some special I/O. It may be some analog to digital converter or anything. It doesn't know that. It's just treating it like a block of external data memory. The same way I might just say move X, the contents of the accumulator, to location 12. It doesn't regard location 12 as having any special significance. It's just a memory location. So that instruction is an instruction which is being used with the 8051, where the 8051 is regarding the outside world. It's just an ordinary block of memory. It's a memory map kind of feature. You might have another instruction. Whoops. Move the contents of the accumulator to port 2. We're specifically naming port 2 now. It's a bit kind of, you could argue port 2 is actually a direct memory address, so let me think of a better one. You could certainly do this with the 8051. You could say, let's not do a move, let's do set B, port 2, 1. You couldn't do that with any kind of generic memory location. Now you could argue, yes, you can do this with some addresses here that would be in the bit addressable memory as well. But this is an instruction that isn't generic, it's more specific. So, if you're doing the kind of MoveX instruction, by the way, the whole sequence of actions required to set the right control signals, to go and fetch the information, bring it back, or to put the information there, is all buried in that one instruction. If you don't want to do it that way, you could still have I can still have my processor here, my 8051, connected to some kind of external device, some, I don't know, could be an ADC or something like that, analog to digital converter, and I could be using ports to talk to it. I might use port 1, port 3, I could use port, and I use those ports to write, to do address, to say which address in here I want to read. I could use some control signals from here, and I could read some information back. What I would be doing, I would write to the ports, and by changing the bits in those ports, it would be switching this on and off and doing things like that, and I can read from certain ports, and because this is enabled and writing out at this point here, I can bring the stuff back in. Basically, the 8051 is talking to the ports, and you happen to have chosen to connect that to some external device. That way of doing something is a kind of port mapped way of doing something. In terms of, now this could be a RAM, that could be a memory, just like the other memory over there, so this could be, but now if I wanted to read from this RAM, I would have to write out here, I'd have to set up this port to write out the address, next I would have to set some control signals, and then I would read back the data. That would be a number of instructions to do that. Whereas in this kind of memory map case, that one instruction does the whole sequence of actions for you. But generally speaking, memory mapped, if you're doing anything that's memory mapped, as far as 8051 is concerned, it thinks it's just talking to general purpose memory. It doesn't know what magical thing you happen to have put at that location in the memory map. In the case of port mapped, effectively the 8051 is, or any processor that's doing this kind of thing, is only talking to its ports. And you happen to have connected those ports to other things, such as external memory and so on. But the 8051 doesn't know there's external memory there. It's basically through a sequence of simple operations, you're configuring these ports, writing to them and reading from them. In the case of the 8051, if you want to do the memory mapped way of things, you have to use port 0 and port 2 to provide the address and the data. You can't choose anything else because the MoveX instruction will automatically fiddle around with those ports. Now if you think, oh, I want to do memory maps, but I want to do it using port 1 and 3, not possible. But that doesn't mean you can't use port 1 and port 3 to talk to external memory, but you can't do it in a memory mapped way. You'd have to talk through the ports to the ports, and then the ports would be connected to the memory. Perhaps it'll become clearer in a little while. Okay, so in general terms, which I've rubbed out now, in memory mapped, the things, the I/O that's connected to your microprocessor just forms part of the main memory map. And all the instructions that you can use anywhere else in the memory map for moving data to it and taking data from it, they work on that as well. So the processor itself doesn't know that there's anything magical or anything special about those particular memory locations. They're just treated like any other memory location. So that's the case of that's the memory mapped case. And it also means all the instructions that you would normally have for doing anything with any general purpose memory location, that all can be used with your I/O, because your I/O is just being treated like any other part of the memory. So it's actually simpler. The other case is the port mapped case, where you have the main kind of memory and you have instructions for dealing with that, and then you have another set of instructions that only deal with the ports. Now, you've got added complexity there, because now you've got two sets of instructions. You've got instructions that only deal with ports and instructions that deal with general purpose memory. But it means the main memory, you get to use the whole of it. There's no part of it that happens to be connected to any I/O or anything. So there's that way too. Now you might say, well, which is better? Well, it depends on the circumstances. And like I say, the 8051 is a kind of a bit of a strange processor, that it has features of both of them, yeah?
Isn't there anything where it's both, like it's got a separate port memory, but you're still using like move to port B and it still knows to put it into the separate area?
Probably. There's probably a whole spectrum of processors out there that have, to a greater or lesser extent, features of these. But I haven't done a survey of different processors but the 8051 sits somewhere in the middle. We're doing this because it may well be, in future years, you might come across the term port mapped and memory mapped I/O. And so you have at least the basic appreciation of, if it's a port mapped case, it's probably going to have, special instructions to talk to it. Often with port mapped I/O, you can actually talk to it at the same time as doing something with the main memory. Again, it depends on the architecture. The 8051 can't quite do that. If it's memory mapped, then effectively the whole of the memory, whether it's connected to I/O or not, the processor doesn't know about it. It's just memory. So, and that's normal for microprocessors. Usually with microprocessors, you can connect them to control the world around you, but as far as the microprocessor is concerned, it just sees everything as just a sea of memory that it can write to or read from. Right. Let's now see if I can convince you about address decoding. Let's say I'm just thinking of how to do this realistically. I might have a 4-bit processor. 4-bit in the sense that it has 4 bits for doing address lines, so 4 bits for addresses. Addressing. So it's not a very powerful processor, so here's my processor, and it has 4 bits. I could connect it, so this is the processor, and this is the, let's say, the memory. RAM. And if it's only got 4 bits for addressing, that means address lines A0, A1, A2, and A3. The number of unique combinations you can have with 4 address lines is 2 to the power 4, which in this case would be 16. So there are 16 combinations of values which are possible here. So from here, talking to that, I could have a RAM that's I've got 16 different locations within it, and I could uniquely identify each of those 16 locations. That's the most I could do. Okay? let's say that, okay, I don't have a RAM that's like that, which happens to have 16 locations. So this is an example of a 16 location RAM. I maybe have my same processor here, so I've still got my microprocessor, my microcontroller, which has still got 4 lines, but I happen to have bought RAMs that each only have 4 locations within them. Now, how many can I have in total? Well, in theory, I can have up to 16 locations, because that's uniquely how many different combinations I can identify. But I haven't bought one big RAM that has 16 locations in it. I've gone for the cheap option, and I've bought simpler RAMs that have 4 locations. Now, because each of these RAMs only have 4 locations, when I buy them, in terms of the address bits for them, they're only going to have an A0 and an A1. Because for that particular RAM, it wouldn't make any sense having an address line A2, because there is no, it only has 4 locations within it. Okay? And this RAM has an A0 and an A1. And this is an A0 and an A1. And this is an A0 and an A1. Now, I have 4 address lines coming out of here. Okay? So let's make it a bit taller. So I've got my A0, A1, A2, A3. Now, I could connect the A0 to that and the A1 to that. And then, depending on the values here, I could be writing to particular locations within that. What I couldn't do, possibly, is if I was to do that, the problem is I could end up writing to both of them at the same time, or reading from them both at the same time. So that in itself now causes a problem. Because we assume, generally speaking, if I'm reading from these two things, they might have different different values of data in here. So if I try and read from them at the same time, the data will become corrupted. Or if I'm trying to write out to them, how do I say whether I want to write to that one or that one? So I need a means of identifying amongst a group of these which is the specific one that I'm talking to. And that's what address decoding is. Address decoding, now you don't need address decoding if you buy a big RAM that has, is the same size as the address space that you can write to or read from.